Okay, so this slide constitutes my entire introduction. So if you have a massive object and a source of light, and the two are pretty well lined up with the observer, then the source breaks up the lens breaks up the light into two images. In general, in the case of microlensing, these images are too close together and small to be seen, to be resolved with telescopes, but the images are bigger than the source, and by surface brightness conservation, therefore, there's more light coming from the images than there would be from the source. It doesn't help you because you don't know how much light is supposed to be coming from the star in the first place, but happily, the lens will go by the source in a reasonable amount of time, like 30 days, and therefore the source will seem to get brighter and fainter, and that's a microlensing event. Therefore, microlensing events are characterized by just three parameters: their time when they happened, their height, and their duration. A little more than about 25 years ago, Alan Paczynski pointed out that you could have microlensing events due to two objects instead of one, and then you get these caustics. Now, you'd think that you would just get two bumps instead of one bump, but there's actually the extra lens causes an astigmatism, and these caustics are similar to the things that you see at the bottom of a swimming pool. As you approach a caustic from the inside, it diverges as 1 over the square root, and then it goes flat. So that would be if you had a point source, but actually all sources are finite, so this gets smeared out by the duration of the source, and you can have these strange curves. So in the case of a binary lens, you get nice big caustics, and in the case where the very unequal mass ratio, which is for planets, you get a little caustic. And so you have to be more lucky to see these bumps in the case of planets than binaries, but anyway, it's a way to find planets. So a year later, Avi and I, working here, looked at this more generic case of planet host microlensing. We noted a couple of generic features. First of all, if this event takes 30 days, we noted that this other bump is going to be shorter by the square root of the mass ratio. So for Jupiter and the Sun, that's 30. So this is 1 day. And therefore, you wouldn't really find these in the kind of microlensing experiments that were going on, which were taking relatively small cameras by today's standards and tiling the galactic bulge, so getting 1 point per night. So then you would only get 1 point on this bump. You wouldn't be able to find anything. And so we advocated at that time having two kinds of surveys, one of which actually found the microlensing events and the other of which had many narrow angle cameras that would try to follow it 24 hours a day. Okay, so it won't surprise you to learn that if one lens can be described by three parameters, then two together can be described by 6 parameters. They don't characterize things by 2 equal bumps, but they get reorganized. And the disappointing fact is that of all these parameters, only one is of direct interest if you're trying to learn about planets, and that's the planet-star mass ratio. The other, another parameter that's of some interest is the separation between the planet and the star, but that is scaled to the Einstein ring, and you generally don't know how big the Einstein ring is. And many of these parameters are just nuisance parameters. But the happy side is that with these 6 parameters, then they're easily identifiable with the features of the light curve, and just by, I can't do it in this talk, but somebody who's experienced can just look at this light curve and tell you what the basic parameters are. So there's a little wrinkle on this that came up a few years later, which is that there's actually a 7th parameter, and that has to do with the caustics. So if the source is crossing a caustic, then it takes a certain amount of time for it to cross it, basically the proper motion, the angular size of the source divided by its proper motion. And so that becomes another parameter. That's how smoothed out these caustic crossings are, and that'll turn out to be important later on. So again, here's an illustration of that. In this case, you have this dip. Why it's a dip and not another bump, I'm not going to go into here. But anyway, there are these caustics, and then right before the dip, there's this rise, and that's because it's going over the caustic. Then it gets in between them. That's where the dip is. But anyway, the duration of this crashing down here is when the source is crossing over this caustic barrier. So that's how you get another parameter. Okay, so a lot of the interest in microlensing is coming from planets. So this is a graph of the planet situation in 2011. It hasn't qualitatively changed since. I've scaled things. Instead of scaling it to AU, I've scaled it to the snow line. So we have a lot of homocentric scientists out there who are very interested in FGK stars. And then the distance from the star sort of automatically gives you the physical conditions of the planet. But in microlensing, most of the stars that have planets that we detect are M dwarfs. And so we want to put our thing on the same scale, physical scale. And so we scale things to the snow line where it's thought that ices and rock combine together to make giant planet formation easier. So in this domain, even though we have very few planets out here compared to, say, Kepler, now Kepler is multiplied by 3 or something. We multiply it by 2, or 3 maybe. But we're totally dwarfed by Kepler detections or even RV detections. But our planets are special because they're in a region of parameter space that other people aren't covering. Yes, these are microlensing planets, Kepler, other ground-based transits, and RV. And these are direct detections. So we kind of have some overlap with RV out here, but basically we're all by ourselves in this region. Yeah, a little less because it's square root of the mass. So they would still be distinct, but they wouldn't be as distinct as on that graph. Okay, so this is just an illustration of how we find planets. So you got a source going by a lens. The lens could have a planet here or a planet here. So there's two images, just like what I showed you. One of them runs around the outside of the Einstein ring, the other one inside of the Einstein ring. If one of these images goes by a planet, the planet's gravity further distorts it, and then you get a bump. If the image does not go by the planet, you get nothing, and then you don't notice it. So it's a statistical method. You're not going to find the planets every time just because they're there if you have a microlensing event. Okay, so that was all theory. Here's practice. This is one of the first microlensing events found. It's pretty much like the theoretical one that Avi and I had. You have a big bump for the star, a little bump for the planet. Here's one that's more or less like the one that Bowden and Schuda wrote about, where it's a central caustic, and you get complicated structure in the center, so it's not reducible to two simple bumps. Anyway, all of these are fairly easy to interpret now. I mean, when we first spotted them, we had more trouble. But the main focus of my talk today is going to be on getting out more information about these planets and also other microlensing events. As I told you, we found the mass ratio. You're thinking that's good enough because you can see the star. So once you see the star, you can estimate its mass. So then you multiply the mass of the star by the mass ratio, you get the mass of the planet. No. In microlensing, you don't see the star. That's the host because it's got a lot of glare coming from, even if you could see it in principle, sitting right in front of a star that's being lensed. If you want to see it, as of today, you'd have to wait 10 or 15 years. Maybe with next generation telescopes, you'll be able to wait 3 or 4 years. But anyway, in general, we don't see them. So starting my very first microlensing paper, I realized that if you could measure two other parameters that are not obvious in this light curve, then you could get out the mass. And here are what those two parameters are. One is the Einstein radius. Okay, so it's clear Einstein radius is in principle observable because you have two images separated by an Einstein diameter. So if you could just resolve them, you could see it. So you can't do it because it's 1 milliarc second. But anyway, in principle, this is observable. Another observable is what's called the projected Einstein radius. So normally people draw these diagrams as I did before. You look at the image, it seems to be out here. But we could draw the diagram backwards and then have some intersection point here. If I'm over here, I've got a perfectly lined up system. And so I've got a very highly magnified event. And so it's obvious that I'm lined up. Suppose I put another observer over here. This observer is right at the edge of the Einstein ring. So they would see an event that was magnified by 1.3 times. So then I would know how far apart the two observers were. And from that, I could measure this parameter. Okay, seems dicey so far. But anyway, I just want to go through the math here, that this angle is to this distance as this angle is to this distance by the small angle approximation. So I've just written that out over here. Then I just cross-multiplied. And then I note that this distance here is, this angle, sorry, is related to this distance by this Einstein light bending formula. And so the product of these two numbers is equal to the mass with a few physical constants in there. So I realized that if in 1992 that if you could measure these two parameters, you'd actually be able to get out masses, and you wouldn't be stuck with just purely statistical information about the microlensing events. And similarly, you can find the source lens relative parallax by taking the ratio. So pretty soon after that, I realized that the situation was close to hopeless because the way that you could get, the only way that you could get this routinely to get the angular size of the source, sorry, the angular size of the Einstein ring is to have a ruler where you have the source as your ruler. It's going to have some known angular size, and then you're going to try to relate this to the angular size of the Einstein ring. Well, the way to do that is to have the source cross over the center of the lens pattern, to cross directly over the lens. Then the duration, the flattening of this curve, tells you how big the source is compared to the Einstein ring. And so then you've got it because you know the source radius, because you know its color and brightness, and so you know Planck functions and stuff. So you can figure it out just from having the understanding where the source is on a color magnitude diagram relative to the clump, which is an observable. So that's great, except if you figure out how big these sources are, they're microarc seconds, the Einstein ring are milliarc seconds. So you've got, this is something that's going to happen about once in 1,000 times. And then you can also, let's see. So anyway, that's the formula there. So then you can also do the same thing with measuring this projected size of the Einstein ring by the following method. So this you have to kind of bear with me. This is my most complicated slide. So here's two stars. Forget about microlensing. We got two stars, the red star and the blue star. Okay, and they're wiggling back and forth here due to parallax and proper motion. Obviously, the red star is further away. And so only people, like maybe a third of the people in the audience, are old enough to remember that there used to be something called relative parallaxes before Hipparcos. And so what we used to do in those days was we would look at the motion of one relative to the other. So we hold one fixed, and then we see this relative motion. So far I have no microlensing. And then in the green line, I show what this motion would look like from the sun because there's no parallax. It's just proper motion. And now I draw a circle around it, which is the Einstein ring circle. So now the source and the lens are moving back and forth relative to each other. And so they're getting closer and further. And therefore, there's all these wiggles in the light curve. And so from those wiggles, then you could derive what this so-called microlens parallax is. And you could derive the direction as well. Okay, and then compared to that on the sun, it's very simple because you don't have any parallax. Now, unfortunately, you notice that this Earth curve doesn't look like any microlensing event that you've ever seen, if you've ever seen any. And the sun curve looks exactly like all microlensing events. So why is that? It's because no microlensing event takes like 5 years, is what's shown here. They take 30 days. And so here you have the same diagram just done in that case. And so they're both going on basically straight lines. And now the sun curve looks like an ordinary microlensing event, but the Earth curve also looks like an ordinary. It might have some subtle distortion in it. We'll get to that later. But basically, it just looks like a microlensing event because the parallax effect is too weak because you don't have time to wiggle like that. You just kind of go like this. So that effect was predicted in 92. It was actually observed in 95. You see this distortion. Here's the prediction. It shows many wiggles. We've never seen an event with so many wiggles, but here, occasionally, like one in maybe 5,000 or so events, looks like this. When you ask how many events look like this, they have enough distortion, you could actually measure the parallax as 1 in 100. So you multiply 1 in 100 by 1 in 1,000, you get 1 in 100,000. So this looks like, it's theoretically interesting, but it's never going to lead to any practical results. Hence, nobody continued working on this problem except me. Okay, so we have a lot of cases of one-dimensional parallaxes. So parallax is a vector. Oh, so you're not used to parallax being a vector because you're into astrometry or something, but it's a vector because, the reason that there's ordinary parallax is a scalar is because you already know how the Earth's moving and you can see the stars moving back and forth relative to each other. But in the case of microlensing, you don't know how the stars are moving relative to each other. So you have to solve simultaneously for the direction of their relative motion and the amplitude of the parallax. And so I'll show you that there's actually, there's only a few of these that are published where you get this one-dimensional structures like this. I'll show you most of the ones that have ever been published. But actually, maybe 10 or 15% of events have this level of one-dimensional information in it. And the reason that they're not published is that they're useless. Normally you have this one-dimensional information. You're actually interested in the amplitude of this vector, okay? So because that's what goes into the mass, but it could be anything. So this is a case where it just so happened that this one-dimensional structure is far enough away from the origin that it's fine. But usually you can't tell anything from this one-dimensional structure. So why is that? It's because if the source and the lens are moving parallel to the Earth's acceleration vector, then the event rises faster than it falls, and you get this distortion. So since microlensing events are intrinsically symmetric, if they rise faster than they fall, this is like fitting a square peg in a round hole. It doesn't work, and you get these residuals. Whereas if it's perpendicular, there's still distortion, but it can be absorbed by the other symmetric parameters. So this is the state of things as they were. Okay, so what can be done about this? Well, one thing is this microlensing parallax is the source lens relative parallax scale to the Einstein ring, which depends on the mass. So if you have nearby lenses, low parallax, or high parallax, or low masses, then the parallax, the microlens parallax, is big, and you can hope to measure it. The other thing is that it's biased towards very long timescale events because, so mathematically, this parallax, the weakest component of the parallax is evolving as time to the fourth power. So it really helps you to have these longer events. It's just a way of saying typical events are much shorter than a year. You can't see anything. So here's a list of events that were examined closely with, wherever it says m equals theta e over kappa pi e, that means it was measured with this parallax method. And so you see, except for this first one, all of these have quite long events, 100 days, 120 days, 68 days, 127 days. These are way off in the tail of the distribution of microlensing events. The one exception, 7 days, is exception that proves the rule, which I'll show you soon. So a number of these events are really very interesting. This is a two-planet Jupiter-Saturn system that was found. And this is a very interesting event just found last year. I don't have time to go into it fully, but basically we saw a little dip here. Maybe you guys can't hardly see it. We got very excited about this dip because it meant that it was passing between two of these triangle caustics and head directly towards the center of the lens system. So we're hoping to get additional information because when it went over the center of the lens system, maybe we could, there'd be more interactions. So then a bunch of amateurs started, getting data over here, and one of them, I think it's this point over here. So he wrote to us. He said, "I have a lot of clouds, but I guess you guys really want us to go after it." So then he was looking for holes in the clouds, and then he got this point. He said, "This thing's gone up by a magnitude, and is that important?" So we, before getting too excited about it, we got the data from him, confirmed that it was gone up by a magnitude. Then we got all these data over here, and so this we were thinking at first, maybe it's some part of the structure reflecting the planet, but no, this is way too big. Any microlens will tell you in one instant that this is a binary, not a planet. So this thing's still a planet. Now you have a binary on top of it. And we had very dense data. Maybe you think it's not necessary. But actually, it turned out there was something very, very interesting about this. Let me, here's a geometry where it's going between these two triangular caustics. That's why it's getting demagnified. Then it heads towards the central caustic due to the binary. The companion of the binary is way further back over here. And actually, if you go back over here, you can see that there's a little bump due to that other binary. So that's a very nice part of the story. But the most interesting part of this is that in this light curve, so you can't tell this by eye, but this central bump here is distorted by the presence of this planet. Okay, the planet is like 10,000 times lighter than the binary, but this distortion is very notable. Because if you try to fit it without the planet being there, delta chi-square goes up by 200. So it's very, very obvious. But more than that, if you eliminate these data here, just excise them and refit the whole thing, but fit it for a planet, you get back the planet with the same mass and the same position as you would even if you didn't see this. So potentially it means that we're very lucky to have this thing pass through here, but If it just gone through the central caustic anywhere, we would have still been able to find this planet. So this particular one is another example. It's a very long event. You know, you can easily see the parallax signal. You know, it's the one dimension that you can see by eye, you can see, but the other dimension you get also. And so this is an Earth-mass planet circulating around a binary star, which the two stars are M dwarfs. This is the only the second such planet. The other one is Alpha Centauri b, which probably isn't real. But anyway, this is the second published planet, whether real or not, of that character.
So this is a planet orbiting one of the stars.
Yes, that's correct. And so it actually is. We're able to figure out that it's you know, the light curves are degenerate between the two cases of circumbinary or circumprimary planet, but because we see this little bump, we know that it's actually separated binary. They're separated by, I think, 17 AU. Well, so this we don't know. I told you before, it could be like 10 planets in the system, but we, you know, oh, so, right, so, but, oh, that's true. So they could, in principle, be yeah. So ask me about it later. It's too complicated. Yeah. Okay. So so another possibility is terrestrial parallax. Okay. So it turns out that these Einstein radii, projected Einstein radii, or Einstein radius on the sky, is typically of order a few AU. This is just a chance. That's the root mean square of 8 kiloparsecs and 1 solar mass with you know, of the Schwarzschild radius of it. But so that means that if you want to be off somewhere else, like I tried to show you, and get another perspective, you should be 1 AU away. But you could be, instead of 1 AU, you could be 1/23,000th of an AU on Earth and try the same thing. So you know, then you expect that you won't see much because it's so you know, such a short baseline. But actually, occasionally you do see something. So in this case, there's a light curve, another amateur going from South Africa, saw a substantially different event than we saw from Chile. Now, it's different because these two times are 8 minutes apart, 1 minute apart, sorry. The width of this is only 8 minutes. Why is the width 8 minutes? Because, what I'm telling you, they're usually 30 days or something, but this is a highly magnified event. So the scale on which we can do a comparison is not the overall duration of the event, but the duration of the peak, which is very short because magnified 2,500 times. And so we're able to reconstruct this. This turns out to be a thick disk brown dwarf. Here's another such event, and you know, can't tell by eye in this case, but anyway, there is terrestrial parallax measurement. So anyway, Jennifer Yee and I were the two people to find such things. And we started thinking, okay, maybe there's many more out there. We should try to theoretically understand how many are detectable. And because this is one of the few levers that we have, you'll see it also for free-floating planets, which are another major issue. And so we did a calculation. You know, here's the two terrestrial planets. There's been like 10,000 microlensing events discovered so far, so 2 of these. We're thinking maybe there should be many more. I won't go through the calculation, but it's analytic. You go through these various different things, and you estimate. And you see that, indeed, we were actually way off between the number expected and the number that are found. So the number expected is only 0.1. So now we don't even understand why we found 2 of them. So, but anyway, this could be a way of finding specialized you know, parallaxes in some special cases. It's especially interesting for free-floating planets. So I suppose this is results about 4 years old, so probably everybody's seen it. But the distribution of microlensing event timescales is basically smooth, and then there's an extra bump here. Okay, so you're thinking we have a lot of unknowns going into this estimates. Oh, so these are, you know, Jupiter mass things. There's 2 of these for every star. But actually, again, this is an eye chart of equations, so I don't want you to go through the equation. I just want to tell you that there's absolutely no way that you can produce that bump without having a bump in the mass function. Okay, it just follows from the most elementary algebraic relations, and so, or you could have bad data or something. But anyway, so those are free-floating planets, and we would like to be able to verify them. Well, so yeah, it just comes from equations. If you know, you just wind up with if you have a smooth distribution of masses in the foreground, then you just end up with a bunch of integrals over the mass and the proper motions and the distances, and you just get pure scale. Right. So like in the disk or something. So if you had, if you had things that are in the bulge that are moving fast enough to escape the galaxy, and there was some huge number of them, yeah, you could do it. But it's basically, the only real assumption is that you have continuity in the distance distribution, and that is fixed because the things are all over the bulge, so there can't be some special populations of things that are very close together in such a hot bulge population. There can be a few that are like that, but you can't have statistically. Okay, so satellite parallaxes. Okay, so satellite parallaxes were first proposed by Refsdale in 1966. So this is like 30 years or something before there's any microlensing events. And you can see from this diagram, you can pretty much understand everything that you need to know about parallaxes. So 30 years later, I independently derived this result, and then I was politely informed by Refsdale that he had come up with this. But one value of doing it independently was that the diagrams are now much clearer as to what's going on. So in physical space, you have some event seen from the Earth. It's going through the Einstein ring. It's giving rise to this light curve. And then the satellite is displaced from the Earth. And so you see a different light curve. Okay, in this case, the satellite is further away, the lens is further away from the source. It's viewed by the satellite. So you get a lower amplitude event, and the peak is at a different time. And so you can measure these peaks, how high they are, and then figure out where the 2 points are in the Einstein ring. Then this vector between them should be related to the distance between the Earth and the satellite, and then you can solve this whole thing. Now, unfortunately, as Refsdale already figured out, and I rederived, there's actually 4 such solutions because these things are vectors here, but you only solve for the scalar separation between the lens and the source. So you don't know whether you have this geometry, for example, or this one, because the satellite could be on the opposite side. And then this distance in the Einstein ring is related to the same physical distance with the satellite, and so you get different answers. Okay, so eventually they did, so try to get NASA to put up such satellites, but anyway, they put up WMAP or some other thing. And so eventually, we got, they put up Spitzer, and Spitzer is like drifting away from the Earth. And so there were various reasons why I thought it would be very difficult to use Spitzer because, it's got 3.6 microns in the Earth. We are observing, 0.8 microns. There's technical reasons I don't want to go into that I thought that this would be very difficult. But anyway, we did manage to get Spitzer to look at this microlensing event in the SMC one time. So, but then they invited me. They went to warm Spitzer, so they invited me to come to a conference where you could explain what could be done with microlensing. And I explained what could be done with it. They said we're not interested because we can't support target of opportunity or something. So I totally gave up on them, and I was convinced by Chaz Beichman to resubmit something off of another thing, which I'll tell you in a second. But anyway, so I made a proposal to get, okay, so you can only observe, Spitzer has an angle restriction relative to the sun, and this is in the ecliptic. So you can do this experiment for only 40 days per year. 38 days for any point in the ecliptic, and we have a narrow range of angles, so 40 days. So I asked for 960 hours of time with this proposal. And I showed, you could get, here's the time you can look at it in different years, and here's how Spitzer looks different from the Earth. This is for a lens that's in the bulge, so small relative parallax, so small microlensing parallax, and so events look similar, but anyway, not identical. And then here's one that's in the disk, so the parallax is bigger. So they, naturally, this creative idea, so the panel, ranked at second quartile. But the director was smarter than the panel, and he gave us 100 hours out of the 960 to demonstrate that this was feasible. And that's actually what I think a rational director should have done, not just give us all the time. And so, here's what we said things should look like. Here's one of these events that we detected last year, okay? So, I've been talking about these things for 50 years, and finally, satellite parallax in a very clear example. And this has, you know, 4 solutions, as I told you. So this is, you know, the 4 parallax vectors. Well, I'm showing 2 of them here, but there's 2 symmetric ones. And then how do you distinguish among these 4 things? Because they're very different. Okay, so if this is scaled to the same distance as this, then you know, the parallax is going to be much bigger, and so it's going to be a totally different solution. So how is it done? Okay, so here's 4 of the solutions presented instead of parallax in terms of projective velocity. So the projective velocity is the lens going by like this, and then so the source sweeps across the observer field of view. So the direction is the same as the direction of the parallax, but anyway, you're dealing with velocities. And so this direction off here is basically the direction of the motion of the galactic disk. Okay, so this is, you know, the galactic disk would be going up like this, so this seems like it's off. But then we measured the source proper motion, which we're not able to do always. And then we were able to predict, given if something was if the lens was in the galactic disk, where would it be? And this is the 1 sigma interval, so this is one of the 4 solutions. So degeneracy is broken. There's more complicated arguments for the breaking this degeneracy, even if we didn't have this information. You know, if you have something that has a small parallax, like this, then you know the two positions of the U naught and T naught are bound to be very close together. But if you have a large parallax, the chance that they're on opposite sides of the center of the Einstein ring in just such a way that they could mimic a small one, the probability of that is very low. So in this case, it's modest, but in other cases, we're able to eliminate all of these things. So before going on to when we looked at many of them, this is the first planet detected this way. It's very beautiful. I mean, it's too beautiful in a way because you have this microlensing event, and then you have another microlensing event that looks just like it, taken from Spitzer and displaced by 20 days. And so it's actually mind-bogglingly difficult to organize these Spitzer observations. This is just a reference to this because Spitzer is uploading on Thursday. They're uploading on Monday for observations to begin on Thursday and then going through the next Wednesday. So this doesn't mean too much to people because they're used to doing observations in advance. But microlensing events are disappearing. You know, you see them, you figure out what they're going to do, and already they're gone. So Jennifer and I, worked to develop a method to do this. But anyway, this is this example. The reason that these 2 events look, almost exactly the same is that the Earth and Spitzer pass perpendicular as caustic structure. So they could have looked actually very different, or you wouldn't have seen the planet at all from Spitzer, and you just would have got the parallax. Anyway. Sorry, so people find the events, but we can't tell what they're doing. They've got some data points that have huge errors, and we're trying to predict if they're going to go up or not. And so we cut off here, and then 3 days later is our first observation, and 10 days later is our second observation. And so, we had to do a lot to convince Spitzer to change their upload profile. We developed a special mode of observation where we have just had dummy coordinates put in there for our 2.6 hours per day, and then we substituted at the last minute. Otherwise, the whole system would have broken down. So anyway, this is a very exciting element of this is that so then we analyzed 22 point lens events, and each one has a distance estimate using that same method that I showed you on the first one. There's only a couple of them where it's really ambiguous. Some are in the bulge here, and most of them are in the disk. And then we can take the cumulative distribution of all these events, and then we can look at the cumulative distribution of planets. Now, the cumulative distribution of planets is a very simple function because there's only one planet discovered in this thing, so we can't say anything. But you can imagine if we had cumulative distribution of events and 5 planets or 10 planets, then we could begin to tell whether planets were more common in the disk or the bulge. So this is something that people don't have any idea of right now. And some people think that massive planets, for example, will not form in the bulge because there's a hostile star-forming environment where maybe O stars were radiating the disk or something like that. So this is an unexplored question, and if we could get more of these, be able to. So I think pretty impressively we got, we started getting we downloaded our data, finished getting it about August 15th, and by December 1st we had 3 different papers already to, actually uploaded and everything to archive so that it could be reviewed by the Spitzer panel, and they were more enlightened this time and gave us all 960 hours. So this is just another binary event, also showing the same feature. Typically, these things, if they're in the disk, they're 20 days earlier than the 10 or 20 days earlier than at Spitzer than Earth, because Spitzer is lagging the Earth in its orbit. Okay, so what actually got me started on the Spitzer was thinking about Kepler. So Kepler broke, and before people had figured out how to fix it, Keith Horn and I wrote up a paper saying that it should be turned over to microlensing. We didn't think that there was any chance that they would actually do this, but I write up a lot of papers like this, telling people what to do, and occasionally they listen. And so, the idea of this was, so in Spitzer we find an event and we tell Spitzer about it and they look at the event. This is not possible to Kepler because it doesn't listen to you. They have to decide 3 months before, then they're going to be looking at something for 80 days, and so you just have to look at a lot of territory. Okay, so nobody had ever thought of doing this before, but actually it's really great for free-floating planets, as I'll show you. So we can't do free-floating planets with Spitzer because free-floating planets last a day, and so we got waiting 10 days for our upload. So that's why we call this multiplexing for mass production of microlens parallaxes. So this is from our paper where we indicate here's a case where 2 planets are seen. So this was just like what actually happened with Spitzer, but we didn't know that yet. So here's what we'd like to do. We'd like to take Kepler and point it right at the dense microlensing fields. So unfortunately, we can't do that because it's stuck on the ecliptic, or actually slightly north of the ecliptic. But we can still capture, when we look at it in detail, a corner of the high-density microlensing fields. And so this is our proposed 5.3 megapixel field for Kepler. There's a lot of other stuff that can be done about this. Remind me to tell you about astroseismology, but it appears, that NASA has accepted this. So normally they accept proposals that you should do something, but in this case, I think they're just going to do it, and they're going to have proposals for people to be on the team. So here's what a free-floating planet would look like if it wasn't a free-floating planet. Okay, so from Earth, it has one of these one-day events that the MOA collaboration saw. And if it was a cataclysmic variable, or it was actually a star, but a very short distance between the source and the lens, you could wind up with one of these short events. But then it would look basically the same from Kepler and the Earth. But if it was actually a free-floating planet, it would look different. So this is the first rigorous test. I showed you this bump. I claimed it was rigorous, whatever. So, but there's no doubt. If we see bumps like this from Kepler and the Earth, there's no doubt that's a free-floating planet. So this is this. We also can get orbits. So we have problem with crowded fields. So Kepler has 4 arcsecond pixels, and this is kind of a mess. But we're working on those methods. Okay, so I'm going to change gears a little bit here. So the ground-based surveys are moving forward. Okay, the Ogle and MOA collaboration both moved towards much wider field cameras, enabling them to get many points per night. So when Avi and I proposed this thing, we said 1 point per night. Here's why we need follow-up. They're trying to get away from follow-up. So my former student, Chung-Ho Han, 10 years ago now, went to the Korean government, and he said, look, there's already a telescope in Chile and a telescope in New Zealand. I would like you to give me $10 million to build a telescope in South Africa. I'll complete the network, and Korea will really be on the map. So he did that 1 year. Then he got turned down. He did the second year. He also got turned down. He figured he was doing something wrong. And so he went back to them. He said, give me $30 million. I'll build 3 telescopes on 3 continents, and Korea will take over this industry. So these are the models, and here's the construction. Okay, so this thing is actually built now. Just started taking observations in February. Okay, we're not into bulb season yet, but this will be the first season, and this is be the coverage. 24-hour coverage during a lot of the time. Well, that depends on good weather in Australia, which is limited. But anyway, the coverage for most of the time. Okay, so I want to move on to WFIRST. Okay, people know WFIRST has several different objectives. One concerns geometry of the universe, one concerns microlensing, and one concerns surveys that are of other people's imagination. What I'd like to do now is, just the motivation for microlensing is that the seeing and weather are better in space, and you can just go much deeper into low-mass planets. And so anyway, the idea here is complete the census of planets by getting to this regime where microlensing can work. But what I want to talk about is a combination of the microlensing and the surveys, namely what will be done for non-microlensing science by the microlensing survey. So if we just consider what's going on here, we have 40,000 images over 3 square degrees with 6 72-day continuous campaigns, so 100 images per day. So one thing you could do is find KBOs. Okay, so right now there's like 2 KBOs or 3 or something out here, and with very poorly determined orbits, sort of 20% orbits. Okay, so WFIRST can find 4,000 to 7,000 of these KBOs with very precise orbits, as I'll show you, and also get many occultations, which are rare, and I'll tell you, why they're rare. So you're thinking this is not even the density of the microlensing fields, but it's a galactic disk field, pretty dense still, in which you might think it's very difficult to search for KBOs, because how are you going to find them among all these stars? Okay. Well, so here's how one was actually found by the Ogle group, and how did they do it? They did it with difference imaging. Okay, so basically just blinking plates. Okay, now this particular KBO was not a new discovery, but was actually found by blinking plates in 1931. But anyway, other ones could be discovered as well. So there'll be binaries. Basically most of them found from light centroid motion, because the astrometry will be incredibly precise. The periods will be extremely precise, so at the break there'll be 0.1% accuracy in periods. You can find many different structures in the KBO distribution. Parallaxes from WFIRST will be incredible. Okay, so there might be systematics which ultimately limit us, but so far I haven't really identified them. So parallax. So astrometry of a single image in this bright regime will be sort of 60 microarc seconds, leading to 300 nanoarc second precision of parallaxes altogether. It's hard to find an application for that, but anyway, even if you have milliarc second or few microarc second parallaxes, you can resolve the depth of the bulge, find structures in it, and so forth. But so 120 million stars with parallaxes under 10 microarc seconds. So this rivals Gaia. So Gaia, is also doing excellent work, but they're confined to the very uninteresting parts of the galaxy. This is the 3 most interesting square degrees of the galaxy. Okay, so this shows the astroseismic window function of WFIRST. Okay, so there's this envelope here, which is much worse than Kepler, but it's still down at 1/10 of a microhertz, so it hardly affects anything. And so you can recover astroseismic measurements for about 1 million stars using WFIRST in this 3 square degrees. Okay, thinking, okay, Plato's going to find this elsewhere, but the stars in the galactic bulge are quite different than the stars, in other parts in the disk of the galaxy, and so it'll be very interesting to compare those. I won't go through this, but anyway, you can find both parameters for those of you who know about astroseismology. And that can also be done, I should mention, for Kepler field. So astroseismologists are now looking at this closely. So most of these are going to be in the bulge, but 10% will be in the disk. So anyway, these are my conclusions. Microlensing is moving to the point where we can find galactic distribution of planets and also individual masses of planets. And we've got a great future ahead of us with Spitzer and Kepler and WFIRST. And